new trends coming up, utilizing GPUs more and more. Some AI-based stuff is out there. We have now demonstrated that we can run these algorithms on real quantum computers with accurate results. With quantum, it really has the potential to solve extremely complex CFD problems. Basically, all of the companies we're discussing utilize COMSOL in some phase of their product design. Of course, there's a lot of answers in the field as well. But typically, those two kind of dominate the market that we are kind of striving for in the first place. So superconductors, MEMS.
All right, let's do this. Welcome to a new episode of the Engineered Mind podcast. Today I have a very special guest, namely Juha, CEO and co-founder of Quanscient. Welcome to the show.
Thanks, Jousef. Happy to be here.
Nice. I think it would be interesting for the audience to talk a little bit about Quanscient in the first place. So what are you guys actually doing and who is Juha? What is your background?
Well, Quanscient is a multiphysics simulation company. We combine cloud and quantum computing to create a multiphysics simulation platform. And who's Juha? Well, yeah, I'm CEO and one of the 4 co-founders of Quanscient. I have a kind of a different background to your typical like multiphysics simulation guy. So I didn't study physics. I studied software engineering and then actually worked as a consultant for 16 years. And in the later parts of my career, I was kind of doing more and more sales-related stuff. So probably for the last 8 years, I spent mostly on sales and kind of doing in roles like business director, where I was responsible for business units, running my own sales team and things like that. Also done a lot of recruitment during my time, or hiring basically, not recruitment per se. And doing 16 years of consulting, you're always kind of building somebody else's vision. And I built a lot of SaaS products for my customers at the time. So I kind of got to know those business models. And of course, it also kind of included a lot of business side consulting. But anyway, I was sort of not actively, but passively looking around for opportunities. And then I met Valtteri, our current chief scientist. And Valtteri did his PhD on computational electromagnetics in the University of Tampere, and then did a few postdocs around the world and ended up in Aalto University as a quantum researcher. And Valtteri was kind of looking at what's happening in the quantum community and quantum industry, and he started thinking that he could actually kind of build a startup around quantum technologies. And that's when we met, because Valtteri was kind of looking for a commercially oriented CEO to help him build the company. Valtteri also contacted some of his friends from the academic days, and our current chief architect, Aser, joined the company. And then we met our CTO, Alexandre. And Alexandre had been building a multiphysics simulation library, open source library. And he was actually kind of dreaming about building a company around that. So that's when the business plan sort of formed, because, Valtteri had even done a publication about how quantum could be used for multiphysics simulations. So it was sort of natural that, okay, we will start building a cloud platform around the open source components or the open source simulation library that Alexandre had built, and start researching quantum algorithms with the technical vision to combine these two into a hybrid solution, which kind of, so eventually our end users could be running multiphysics simulations without necessarily even knowing if it's running on quantum hardware or classical cloud hardware.
I see. That's super interesting. Though, what was the vision, or why did you see the need of quantum simulation in the engineering space? I mean, there's a lot of cloud-based simulation providers out there, obviously, as some of the listeners might know. What was your vision, or what's the mission and vision of Quanscient to solve in the engineering industry?
Well, with quantum, you can do things that are just impossible with the cloud. So basically, what we've started with quantum is CFD, because that's a tricky problem. Of course, it's moving forward at a rapid pace. There's like new trends coming up, utilizing GPUs more and more. Some AI-based stuff is out there. But with quantum, it really has the potential to solve extremely complex CFD problems in a fraction of the time. So for example, let's say very accurately solving a aerodynamics of an airplane, which is a pretty unsolvable problem, even with like cloud scaling and GPUs and all that with CFD at the moment, with enough accuracy. Of course, you can do it in a more rough scale, or you can simulate, let's say, like a single spoiler very accurately. So kind of really entering these new realms and enabling completely new use cases for simulations. And actually, you mentioned there's a lot of cloud-based providers, but when you think of multiphysics providers who can combine computational electromagnetics, solid mechanics, and computational fluid dynamics, there's not so many anymore. So it's still kind of a field dominated by kind of desktop-based technology.
Yeah, it's true. When we talk about specific use cases, but maybe before we jump to how actually kind of on a high level quantum simulation works, what are some of the use cases where you see a tremendous increase of like acceleration in computing? I mean, if you go to your website of Quanscient, we see MEMS and superconductors, which are like the two main use cases. Maybe you can explain what you see there in terms of like speed and accuracy.
Absolutely. So yeah, it's, as said, our simulation platform is a multi-physics simulation platform. So technically, we have capabilities to do a lot of things. But as a new company entering the market, it's necessary to focus in the sales and marketing wise. And we chose superconductors for one reason. We have a lot of in-house expertise in modeling superconductors. Basically, that's what Valtteri did his PhD on. And we actually have a couple of other people too who have done their PhD on superconductors. So we had tremendous knowledge on the subject. And superconductors are extremely tricky beasts to simulate. They're by nature very nonlinear. There's a lot of complex problems such as like quenching, AC loss modeling. And to do that accurately in 3D is an extremely slow and complex simulation. We have an publication that we did in collaboration with MIT about this, where we did a 3D simulation on AC losses on a superconductor for a fusion energy related company. And they were running those simulations in a desktop-based solution using a 96-core high-performance computer. And it actually took them 8 days to run this one simulation. With Quanscient also using 640 cores in the cloud, it was running 1.5 hours. So that's a speed up of over 130 times. So kind of these are the sort of impact we can make on the superconductor side.
Yeah. What are we talking about pricing? Maybe if I could chime in. Like, how does the pricing model, for example, work? Let's say I'm going to sign up for your platform. Maybe there's a trial, maybe there's not. How do I get started, and how does the pricing model work? Is it just a pay-per-use, or like, how does it work?
So it's a subscription-based B2B SaaS. So essentially, our users purchase a set amount of core hours, either with a monthly package or a yearly package. And when the simulations are running, the quota of core hours gets consumed. And what's a core hour? So let's say you're running that big superconductor simulation. You're running it on 640 cores at the same time, and it lasts for 1.5 hours. So you end up consuming 960 or something to that range. I'm not too good at doing math on my head. But anyway, so you end up consuming less than 1,000 core hours. So that's how it basically works. And let's say, okay, with a package of 120,000 core hours annually. So basically what it means that you can be running simulations nonstop parallelly using about 14 cores simultaneously for the entire year. So that's a huge volume of simulations actually. And in the pricing model, we have no limitation on the number of users. So the only thing so basically it scales according to your need of simulation. So it's extremely flexible in that sense.
I see. When we talk, maybe going a step backwards, talking about quantum simulation, how does it work from first principles? Maybe not like going super into technical details, but maybe from first principles and how it maybe differs from classical CAE simulations, because we all know this FEM, FVM, and what else we have, like Lattice Boltzmann, whatever, maybe just from a very high level.
Absolutely, yeah. So, I mean, traditionally, if you think about multiphysics, it depends on linear algorithms. So, I mean, you have some kind of discretization method, like the finite element method, FEM or FVM or whatever. And then you end up solving partial differential equations. Now, this is something that has been trialed in quantum a lot. And when you do this in quantum, you need some kind of a quantum linear solver. And there are two existing methods, like the HHL, and that requires basically fault-tolerant quantum devices, which are still, the best estimates say, about 10 years away. And then there's a variational approach, which can already be used in these current NISQ-era devices, NISQ meaning noisy intermediate scale quantum computers. So basically, they're noisy, they make a lot of errors in their calculations, intermediate scale, so they're quite small and limited in the number of qubits. But the main problem with any of these methods is data input and output. So because there's no quantum memory, quantum RAM, you cannot input an arbitrary matrix into a quantum computer. And you can't read the full solution. You can only extract, for example, some global properties like the integral of the solution.
Yeah.
So what we actually do is we put our efforts into what we call quantum native methods. And a couple of examples of these are the quantum lattice Boltzmann method. I mean, the lattice Boltzmann method is a pretty well-known CFD method. And these quantum lattice gas automata. And basically what we mean by quantum native is that we try to encode the physics directly into the system so that we have kind of a direct analogy between the physics problem and the evolution of the quantum computing system. And that has kind of a few advantages. So basically we can, with the quantum native approach, we can get rid of the data input problem, because the kind of the probabilities of the lattice Boltzmann method, if you're familiar with it, you kind of know it's got to do with these mesoscopic particle densities and their probabilities. These can be encoded directly into the qubits of the quantum circuit. And that also means that we can increase the size of the lattice or the size of the problem exponentially as the number of qubits increase. And the other key advantage is that when we read out the data, the qubit measurements correspond directly to the probabilities of these densities in the lattice, and this data can be turned into the full solution just with a simple summation. So that's kind of the jinx of it. It's really, of course, intense mathematically, and hard to explain in a kind of this, let's say, ground level terms easily.
Yeah, I think from a software engineering perspective, then I think it's actually a really cool thing to actually take something so complex that's working like in a complex way behind the scenes, taking it, putting it into a user interface that's actually easy to use for an engineer who has no idea how quantum simulation works. And maybe you can explain how that was, like in terms of UI and UX for the engineers, or like for people using your tool, how difficult of a thing that actually is to build a product that takes away the complexity and makes it as easy as possible for engineers to use at the end of the day.
Well, where we are at the moment, of course, is that the cloud product and the graphical user interface we have in the cloud does not yet contain any quantum algorithms. So basically, it's cloud only at the moment. We can already achieve these like over 130 times speedups that I mentioned with that. But with so the quantum part is more R&D phase. We do have a interactive browser-based demo about that actually available, which kind of showcases the quantum algorithms, and you can do some experimentations with them. But kind of how this will be integrated, I mean, of course, the methodology we use there is different. Currently in the cloud, we use finite element method based. And this is, well, lattice Boltzmann or lattice gas automata, so it's a different method completely. How it will exactly work, we don't know yet. And that's fine, because there's still kind of also the quantum hardware needs to evolve before we're at a level where we can actually solve these problems that kind of provide true business value with quantum. We have now demonstrated that we can run these algorithms on real quantum computers with accurate results, but it's not quantum advantage yet. These problems are kind of like in the simpler scale at the moment, and they can be solved with classical computing, of course, kind of quite fast actually.
Yeah.
But the math is solid. So basically, with, let's say, between 60 to 80 effective qubits, we can already solve problems that are pushing the limits of what can be done on classical hardware. So it's actually not distant future. It's a couple of years away.
That's pretty amazing. What are you doing in terms of academic applications and maybe research frontiers in terms of like, what do you think is the next big thing? Obviously, we talk about a couple of years until it's being ready, like the full quantum simulation thingy that we've talked about. But then also, what does the future bring in terms of quantum simulation? It's like full end-to-end simulation. How do you see the future evolving there?
Well, as for academics, so our mission is to create publications and kind of help support the scientific community and contribute there. Of course, we're a company, so we also want to generate IP and create like patents on this. But after that stage, we do want to contribute and share the information, make the publications. As for how I see kind of how this ends up being is that I think we're still a very, well, as said, at least 10 years away from the full fault-tolerant quantum computers. And even at that point, I don't think they will be, in a way, universal, so that quantum computer does everything. There will always be a classical computer. Well, never say always, but there will, for a long time, there will be a classical computer that's kind of the interface to the quantum computer. And there will be an era of this like hybrid computing, where cloud computing and classical computing will run in combination with quantum computing, and kind of quantum, or you could kind of think about it as sort of like CPUs and GPUs work in collaboration. So GPUs take care of the stuff that they're good at, CPUs take care of the rest. So just replace G with Q. You have QPUs. And the QPUs handle kind of the stuff that they shine in.
Yeah, but it's maybe the same story as with AI, because a lot of engineers think about, okay, will AI replace me? Forgetting that it's actually more like a productivity tool in their workflow. So maybe in the future, quantum simulation will act more as like kind of front-loading simulations to get quickly results, and then see where the classical simulation would fit into the classical engineering workflow, so to speak.
Absolutely, so, yes. And of course, they're like, okay, you mentioned AI, so that's, of course, one trend here. And the same applies for this. So kind of it's a tool for engineers to make their work more efficient and kind of help them create more efficient and better designs.
Absolutely. When we talk about the democratization, what a lot of people love to call it, of maybe quantum simulation, what steps is Quanscient taking? Like, would engineers be able to just sign up for a trial? Is it already accessible like as a trial? Can people just go to your website and say, hey, I want to give this a spin? As we've talked about earlier, how does it work? What can people actually consume from you guys to actually get started or maybe learn more about quantum simulation?
For the quantum simulations, I'd like to invite people to visit our interactive quantum demo. So we can share the link in the description, I guess.
Yeah, definitely. Yeah, that's good.
So
cool. Then,
yeah, and of course, on the cloud side, we have we invite people to get in touch with us, contact us, and we can schedule a demo about it to kind of figure out how it fits your industry problem and simulation use cases.
Yeah. Would you say picking an optimal use case at the moment for Quanscient AllSolve, how you call your solver, like is the main thing that, exactly right? The AllSolve is the main solver that you're using. If someone has a use case and is not sure if they should come to Quanscient, do you think every multiphysics problem is a good use case for your platform? Or do you think there are some criteria that have to be fulfilled?
It's technically very versatile. It has a tremendous number of capabilities. On our website, you can find a lot of the use cases we can do. But of course, as said earlier, kind of commercially, the main focus area for us and where we kind of push for creating this use cases and benchmark are superconductors and MEMS. And we didn't talk about the MEMS side so much yet, but for MEMS, we like to talk a lot about design of experiments. So basically, MEMS differs superconductors in a way that there can be very complex simulations there, but not necessarily something that takes like 8 days. But design of experiments is a method for kind of reducing the number of fabrication runs that MEMS designers need to do to optimize kind of realistic device performance before launching the product tapeouts. And that requires intense finite element method simulations, which should not be blocked by constraints about size, capability, throughput, hardware, or even licensing. So for MEMS, Quanscient also removes these barriers. So we enable MEMS companies to do these production level simulations on the later stage, where running simulations with massive volumes is a requirement to kind of optimize the product, reduce the number of fabrication runs that are needed kind of to finally arrive at the production level design.
Yeah, I mean, when we're talking about the quantum simulation space, we've talked about it in the beginning. Kind of the field is rather small. If we talk about cloud-based simulation technologies in your space, who's at the moment your biggest competitor? Is it ComSol, would you say, in the multiphysics space?
Well, yes, we run into a lot of ComSol users, absolutely, and basically all of the companies we're just discussing utilize ComSol in some phase of their product design. Of course, there's a lot of answers in the field as well, but typically those two kind of dominate the market that we are kind of striving for in the first place. So superconductors, MEMS. We also do have clients using Quanscient also for example, electric motor design, or even superconducting electric motor design, which is actually a really interesting sort of rising trend in electrifying aerospace, kind of more efficient electric motors that could allow for longer term electric powered flights.
That's really cool. When we talk about answers, ComSol. So the CAE market is a multi-billion-dollar market, which is enormously big. But how do you? I mean, first of all, like props to you guys that you actually take the decision and build such a product and go into the market, which is super, super competitive. So what do you think is like some of the learnings that you already have, like by building a startup? What are the things that you would recommend someone to do if they also want to build their own startup, not necessarily quantum simulations, but maybe another startup? What are the things that you maybe advise people not to do?
Yeah, it's definitely not the easiest market to enter. So there's a lot of kind of existing products out there who have a really good market position and have been around for a long time, and the users they've sort of solidified their position on the companies. So I think a requirement to enter this market is that the new product can't be twice as good or even 5 times better. It needs to perform at least 10 times better to even have a chance. Because introducing a new FEA tool is, of course, companies always see risks there. Is it accurate enough? Does it match our measurement results? Does it match our current simulation results? So you need to prove these things, and you need to prove you're 10 times better, at least 10 times better, to be able to cross that barrier. But as for what to do, so one, talk to a lot of potential clients even before you have the product. Well, this is not specific to FEA market. It's kind of for any startup. But really get validation that you're building the right thing, and learn about the market and learn about where you should initially focus your product on. Talk to other entrepreneurs. They are surprisingly, well, I don't know surprisingly, but the startup community kind of helps each other. So just get help, get support, get sparring, get tips. People, if you ask for help, you typically get 30 minutes of their time, and they might provide very valuable pointers. And kind of lastly, what has been pretty effective for us is that, let's say you do a pilot with a bigger corporation. So design these pilots with an opt-in for the SaaS subscription, or whatever your business model is, subscription. So let's say agree that if we reach technical objectives A, B, and C, this pilot will convert into a commercial agreement.
That's interesting. And from a personal perspective, like when you started building the company, what are some of the things that you absolutely dislike and some of the things that you like building a startup? I think, yeah, because I've been only working in startups so far, also like in bigger companies for internships, but like mostly startups, would be interesting to hear your take on that.
Well, I haven't regretted once. It's been just constant learning. So just like a wild trip, absolutely. But of course, it's intense. So kind of finding the balance between work life and running the company is challenging. But I think it's something you have to do to a degree. At least I have family, so I do want to spend some time with them as well. So just creating some limits that you don't cross, kind of that it doesn't get like unreasonably all work, because that's probably something that you would regret eventually. Like if
Definitely, but how do you manage that on a personal level? Do you have some kind of blockers where you say, okay, after 5 p.m. I'm gonna leave my desk, I'm gonna go home, or how do you do that personally? Because I think it's kind of it's a tricky thing, because you always think I could have done more maybe that day, like at work. It's how do you do that?
Yeah, I use blockers. Yes, so I use blockers for, let's say, do sports. It's a blocker in my calendar, and I will do sports at that time, because that's one thing that kind of keeps me going. It helps me recover. I also I use blockers also in the evenings when I have like family engagements or something like that. So I make sure that I'm available at those times. And I was supposed to say something else too, but now I forgot. You need to cut this
Maybe
out.
also the flip side of the things, like things that you maybe wouldn't advise people to do. We talked about work-life balance. Then what about the finance? Maybe you want to talk about the founding side of things, like how tricky that might be if people want to get funding rounds, maybe Series A, Series B, pre-seed, and all these kind of things. I mean, you had your Series A now, if I'm not mistaken, recently.
It was the seed round. Yeah, we raised 3.9 million seed round. Yeah.
Exactly. How was that for you as a feeling?
Well, of course, in the current market situation, it's challenging. But kind of when you find the right investors, so talk to a lot of investors. Also, kind of investors typically give you recommendations. If you're not a right match for them, if you ask like, who do you think would be sort of who should we be talking to? They do help. They kind of give these pointers, and once you find the right investors who are able to support you in other ways, financially too, so it's after that things kind of move quite quickly. So, and of course you have to have a sensible business model. You have to have a great team. You have to have these basic building blocks, but like it's very doable even in a bad market situation. But of course it does eliminate a lot of companies, but then again, the ones who kind of get through these times come out way stronger. So, and I really believe we're one of those.
I like the confidence. That's good. So if also people want to check out more in the description, I'm going to put every link that's relevant for people, our listeners, down in the description, to the demo, other resources and everything else. Also the LinkedIn link from Juha. If you want to reach out to him, send him a connection request. And then, everything else you will find in the description. And now closing remarks, maybe motivating last words from Juha to the engineering community.
Do reach out. Happy to connect on LinkedIn. And also, if you're interested, if you feel Quanscient also might be something you want to try, don't hesitate to get in touch about that as well.
Excellent. I think there was a very good initiation in terms of a podcast to have like a first episode to just talk on a very high level what quantum computing is and what the potentials might be, maybe also limitations and disadvantages. But we'll certainly have a second part, hopefully in the future. So in a couple of years, Juha, if you made a big breakthrough, definitely come back to me and then we could do a second part for the engineering community. So thank you so much.
Thank you so much, Jousef. It was a pleasure. And definitely, let's do a sequel.